Good morning. So let us continue with the theory of biopropagation course. We will now see the second module, review of thermochemistry, chemical equilibrium and kinetics. So thermochemistry starts with the topic called stoichiometry. The stoichiometry is the science used to determine the amount of oxidizer, which is usually air, that is required to completely burn 1 kg of fuel. When I say completely burn, and I take a hydrocarbon fuel which has a carbon and hydrogen in some proportion, you will see that all the carbon in the fuel should convert to carbon dioxide and all the hydrogen will convert to water vapor. So, for doing that, what is the amount of air required? That has to be evaluated. Obviously, it is a theoretical value. So, we have seen several types of fuels that contribute to fire. They are mixtures of saturated and unsaturated hydrocarbons. Basically, they have carbon and hydrogen atoms. In many cases, we have seen some numbers of nitrogen, sulfur and O atoms also in wood and plastics, etc. So now, in this, carbon and hydrogen are the fuel elements. Oxygen in the fuel will contribute to the oxidizer directly. Normally, nitrogen and sulfur will be inert. So, in the stoichiometric calculation, we will find the theoretical value of completely burning the fuel to carbon dioxide and water vapor. We will not be able to, or we will not consider the formation of nitric oxides, sulfur oxides, etc. One more thing is, if the fuel has oxygen atoms, then the external oxidizer like air requirement will reduce. Now, coming to the air itself, we will consider the composition of the air to be 21% of oxygen and 17% of nitrogen by volume. Even though there will be impurities like argon, carbon dioxide, etc., but they will be in traces, so we will not consider them. So, let us see an example. Consider a general fuel which is just a hydrocarbon containing X atoms of C and Y atoms of H, and the global single step reaction considering 1 kilomole of fuel CXHY can be written as CXHY plus A times O2 plus 3.72 N2. So, this is reactant side. Now, please see here. This is oxygen 1 mole plus 3.76 times of N2. The mole fraction of oxygen is 1 by 1 plus 3.76, that is 0.21. So, the standard air, as I told, the volume fraction is 0.21, which is same as the mole fraction. Okay, so this A times O2 plus 3.76 times N2 says that there are A into 4.76 times of air present in the reactant. 1 kilomole of oxygen or 3.76 kilomoles of nitrogen into A times, which is required for complete combustion, is present in the reactant side. Now, coming to the product side, all the C atoms should convert to CO2. That means X times CO2 will be formed. Similarly, there are Y hydrogen atoms. So, Y by 2 H2O molecules will be formed. As I told you, nitrogen is kept inert. That means A times 3.76 into nitrogen will be there in the product stream. So, this is called global single step reaction written in terms of 1 kilomole of fuel. This is the usual way we write the chemical reaction, considering number of moles of fuel, that is 1 kilomole of fuel plus whatever be the amount of oxygen required for that. But this oxygen will come through airstream. One more point here is, if you say the reactants number of moles, this is not equal to molecule. Please understand that. If I say 1 kilomole of fuel, it has several molecules of the fuel. Similarly, when I say A moles of O2, it will be several molecules of O2. So 1 kilomole will have several molecules, and this equation is not molecular level equation, it is a molar level equation written in a single step, which indicates the reactants which come into the reaction zone and the products which are formed. Again, we have not considered the dissociation of CO2, H2O, etc., because it is a theoretical calculation where we assume complete combustion has taken place. Now, how to find the value of A? That is done by balancing number of atoms on both sides. So, for example, in the left side for O2 I have A, the right side for O2 I have X plus Y by 4. So, the value of A will be X plus Y by 4 for the hydrocarbon CXHY. If it is CH4, then it will be 1 plus 4 by 4. So, A will be having a value of 2 for methane and so on. Now, the stoichiometric air fuel ratio, that another important quantity, is defined as the mass of air required to completely burn 1 kilogram of fuel. Please understand that this is global reaction which is written in terms of 1 kilomole of the fuel. Now, we are defining another quantity which is stoichiometric air fuel ratio, which is the ratio of the mass of the air required to completely burn 1 kilogram of fuel. This is done because the mass is conserved. Mass of the reactants will be equal to mass of the products. So, in mass basis, if you write, then it will be useful for us later. So, A by F, that is air to fuel ratio, the suffix St indicates that it is stoichiometric air fuel ratio, which is nothing but the number of moles of air first, 4.76, 1 plus 3.76 into A into 28.84 is nothing but the molecular mass of air. Molecular mass of air. This can be found by the product of mole fraction of oxygen into its molecular weight plus mole fraction of nitrogen into its molecular weight, that is 0.21 into 32 plus 0.79 into 28, that will give 28.84. So, 4.76 A into 28.84 is the mass of the air required to completely burn. Now, 1 kg of fuel, how, this is 1 kilomole. 1 kilomole into molecular weight in kilogram per kilomole will give the mass of the fuel. So, that is nothing but, what is the, this is 1 kilomole into molecular weight of fuel is nothing but 12 times X plus 1 time Y. This 12 is the for the carbon, X is the number of carbon atoms plus 1 into Y, Y is the number of hydrogen atoms. So, 12X plus Y is nothing but the molecular mass of the fuel into 1 kilomole, that will give you the mass of the fuel. So, this ratio is mass of the fuel, mass of the air required to completely burn 1 kg of fuel. Stoichiometric air to fuel ratio. Now, in general, in fire or in any burner, oxygen supply will not be exactly same as the stoichiometric value. In some cases, we will give lesser amount of oxygen required along with the fuel. That is called oxygen starved case. In this case, the oxygen will be lesser than that required for complete burning. So, the value of A will be less than the stoichiometric value. What happens? Complete combustion will not occur. So, that is carbon dioxide formation will be partly done, but partly CO will be formed. Similarly, H2O will not be complete. Some OH, H also will be there in the product. That is one of the important problems. When there is no enough oxygen, then incomplete combustion can occur. This is seen in several fire scenarios. Basically, when a fire is within a compartment, not enough oxygen can come in because of ventilation conditions. So, we will see that pollutants or incomplete combustion products are seen. In the cases of oxygen starved combustion or when dissociation of product occurs at high temperature, we cannot just use this global equation to write. For example, in the right hand side, I can say XCO2 very easily. But if there is CO also, part of CO is formed, part of CO2 is formed. See, for example, in the X atoms of carbon, say, let us say, some amount of carbon is converted to CO only, remaining is converted to CO2, then how will you find the difference between the number of moles of CO and CO2? It is not possible only with the information what we wrote in this particular equation. So, we need to go for second law of thermodynamics in order to identify or evaluate the number of moles of these species. For that, the global reaction is not only sufficient, we need additional equations or molecular level reactions to solve the problem, which we will deal little bit later. In this case, we use the second law of thermodynamics and evaluate the product mixture at a given temperature and pressure. Now, in the second case, oxygen rich burning, the air availability is higher than A kilomole. Okay. Then what happens? This actually is seen in open fires or very good ventilation occurs when the fire is going on. In this case, the excess oxygen will be seen in the product mixture. So, that is the main difference here. In these basic cases, we can apply whatever be the conditions required can be evaluated based upon the ventilation. That is what the main purpose here is. So, if the ventilation is not good, then we go for oxygen starved condition. If the ventilation is good enough, then we go for excess oxygen conditions. So, that means always we will not be able to see only the stoichiometric condition, theoretical condition. In many cases, there will be oxygen starved, and in many cases, it will be oxygen rich condition. So, a useful parameter called equivalence ratio can be defined as the ratio of the stoichiometric air to fuel ratio to the actual air to fuel ratio. Please understand, stoichiometric air to fuel ratio is the theoretical value of the mass of air required to completely burn 1 kg of fuel. Actual air fuel ratio is what is the amount of air actually has participated in the reaction, that mass of that divided by the mass of the fuel. So that ratio is the equivalent ratio. Phi, we can say phi equal to stoichiometric air to fuel ratio divided by the actual air to fuel ratio. Now, let us consider an reaction where the excess oxygen is considered. However, dissociation of CO2 is also considered. Okay, so the fuel here is C7H16 heptane, and 13.75 is the value of A here in this equation. Please understand how much is required. This number of moles of air is required is 7 plus 16 by 4. So you can go back, x plus y by 4, that is the value of A. So here it is 7 plus 16 by 4, it should be 11. So A, stoichiometric value of A will be 11, but as I told you, we have considered excess oxygen, it is now 13.75, which is more than 11. So we expect, if there is no dissociation, we don't expect CO. So I can say 7 CO2 and I can say 2.75 O2. So the equation is straight away closed if there is no dissociation. But what we are now seeing is, we are considering dissociation of CO2 also. That means CO2 gives CO plus O2. That is also happening. So now it is very tough to determine the value of A, B and C only with this equation what we have here. So let us try to attempt it. Let us say C balance. 7 is in the left hand side, in the right hand side I have A plus B, correct, that is one equation. Then H balance, not quite useful here because H is 16 here, right hand side also is 16, so it is closed. So let us take O balance. O2 is 13.75 in the left hand side. Here in the right hand side A plus B by 2 plus 4 plus C. So now you have only two equations and there are three unknowns. To understand, when there is a dissociation, then it is not easy for us to just consider one equation and finish it, because there are three unknowns in this equation and only two equations we can generate due to the atom balance. So nitrogen is straight away conserved, hydrogen is straight away conserved. So only we have carbon and oxygen balances coming in, which can give us two equations, but we have to solve three unknowns. Okay, so in this case 11 by 13.75, that will be the equivalence ratio. So if the equivalence ratio is less than 1, then more air is present than the required or theoretical air. Do you understand? So you may wonder that since excess air is present, why there should be CO? CO should also oxidize to CO2, correct? But this CO is not due to incomplete combustion or due to insufficient or oxygen stored condition. Insufficient oxygen or oxygen stored condition. This CO is due to the dissociation of CO2 because of the fact that the temperatures are quite high, say more than 1900 Kelvin and so on. So to calculate the values of A, B and C in the product mixture, a concept called chemical equilibrium is used. Okay, so on one hand we have the global equation which is written in this form, where globally, or a mechanism, or totally what is the reactant site species and product side species are listed in one shot, in one equation. But we also need elementary equation or elementary reaction which is defined for several processes. Taking into account of CO2 dissociation, I can say CO2 dissociates to form CO plus half O2. Please see this reaction as double-sided arrow, indicating that this is a reversible reaction. A global reaction is only one way. Once the products are formed, no way the reactants can be formed again. That is, this equation clearly is one way. Heptane reacts with air to form these products. There is no way these products can recombine to form heptane and oxygen again. That is the main difference between the global reaction, which is molar based reaction, which is only one sided. Coming from the reactant side goes to product side, and the reactant side is just the fuel plus whatever be the oxidizer mixture. Coming to the elementary reaction, considering say CO2 dissociation, you can see that CO2, a double sided arrow is given here, giving CO plus half O2. Here this is a reversible reaction and also molecular level reaction. As I told you, this reaction, global reaction, is read as 1 kilomole of heptane plus 13.75 kilomoles of oxygen plus 3.76 nitrogen, giving A kilomoles of CO2 plus B kilomoles of CO plus 8 kilomoles of H2O plus C kilomoles of O2 and 51.7 kilomoles of N2. So that is the way I read this. When I read this elementary reaction, I say one molecule of CO2 dissociates to form one molecule of CO and one atom of oxygen. So this reversible reaction is called elementary reaction, molecular based reaction, and the rate at which the forward reaction takes place and the rate at which reverse reaction takes place are dependent on a given temperature and pressure. Okay, at a given temperature and pressure, there can be a equilibrium condition at which definite amounts of CO2, CO and O will be present, or O2 will be present in the mixture. Okay, so when the pressure and temperature changes, this composition will also change. Do you understand? The rate at which the forward reaction takes place will match the rate at which the reverse reaction takes place at a given pressure and temperature condition. And the products, say for example, in this case I can say if the temperature is 1950 Kelvin and the pressure is 1 atmosphere, I can say about 2% of CO2 as dissociated. I am just giving an example. Then I can say the products 98% of CO2, then the remaining 2% will be contributed by CO and O2. So to find the exact composition, we have to go for chemical equilibrium study, which is based on the second law of thermodynamics. Chemical equilibrium. So what I do with this here is, I take this elementary reaction. This is only one example. I can take several elementary reactions which are basically available for us. See, for example, in this case I have taken CO2 giving CO plus half O2. So even higher temperatures, if we go say more than 2200 Kelvin etc., H2O also can dissociate to form H2 plus half O2. So I will write here H2O dissociates to form H2 plus of O2. Please see here that this is another elementary reaction. Elementary reaction, again I can read this as one molecule of H2O dissociates to form one molecule of H2 and one atom of oxygen. So, as I told you, at a given temperature and pressure, this reaction also will be in equilibrium, particular equilibrium. That means there will be definite amounts of H2O, H2 and O2 will be there in the product mixture. So, how will you go for finding the composition? For that, I basically use the concept of chemical equilibrium, which actually enables us to find a equilibrium constant Kp. The K suffix P indicates that this is the equilibrium constant defined with respect to partial pressures. I will just tell it about that later. So, Kp is the partial pressure based equilibrium constant. So, to find this, I need to calculate what is called Gibbs free energy of all the species, all the components in the mixture. Gibbs free energy, specific Gibbs free energy small g is defined as specific enthalpy minus temperature in Kelvin times specific entropy. This is the definition of the Gibbs free energy. Any free energy can be considered as the potential available for a particular species. It is also called chemical potential. Gibbs free energy is also called chemical potential. Okay. So, when the reaction occurs, the Gibbs free energy of the reactants are reduced and that of the products are increased. Okay. So, the Gibbs free energy of individual components are found and the mixture also can be evaluated later. So, using that we will find the composition. The procedure is very simple. I am not going to go to all the details. So, here what I first do is I define the Gibbs free energy and I apply that to the any elementary reaction like this. So, the equilibrium constant based on partial pressure Kp is expressed now in terms of molar Gibbs free energy change delta G. Okay. So, what is delta G? Delta G is defined here is equal to, in context of this same reaction, product side species are CO and of O2. Reactant side species is CO2. So, I can say delta G will be equal to 1 kilomole of CO. So, 1 kilomole into GCO overhead bar indicates that this is molar based quantity, that is per kilomole, specific per kilomole at a given temperature and the atmospheric pressure P0. P0 is the atmospheric pressure. So, it gives free energy, molar Gibbs free energy of CO calculated at a given temperature T and the atmospheric pressure P naught, that into the number of kilomoles of that species plus oxygen. The product side I am first taking 0.5 into Gibbs free energy of molar Gibbs free energy of O2 calculate the temperature T and pressure P naught. So, these two terms combined is nothing but the molar Gibbs free energy of the product or Gibbs function of the product minus, I go to the reactant side which is CO2 alone. So, 1 into G bar of CO2 calculated the pressure P naught and temperature T. So, this Gibbs energy change or Gibbs function change is nothing but the Gibbs free energy of the products minus Gibbs free energy of the reactant. For the reaction written in this way. I can also write the reaction in the reversed way. CO plus half O2 giving CO2, that is formation of CO2. The reverse reaction of the dissociation will be the formation. Correct. So, if I do this, then you will see that this delta G will change its sign. There is no problem in that. See, you first write the elementary reaction in whatever way, either as a dissociation reaction or the formation reaction, no issue. But based upon the way you write, you please define delta G. That is the main purpose here. Okay, now here P naught, as I told, is atmospheric pressure, standard pressure. But reaction need not occur always at the atmospheric pressure. It may be occurring at a different pressure, say P. Okay. Mole fraction of any species or any component in the mixture, which is xi, ith component, can be defined as the partial pressure of the ith component divided by the total pressure P at which the reaction is taking place. Do you understand? So, that is the definition of mole fraction. Partial pressure divided by the total pressure. Now, Kp can also be defined in this way. So, please understand that first of all I have taken delta G calculated as the Gibbs free energy of the product minus the Gibbs free energy of the reactant. Using that, I can find the value of Kp as exponent of minus delta G, which is calculated at a given temperature T and atmospheric pressure P naught divided by universal gas constant Ru times the T. So, this expression says that Kp is a function of temperature only, because delta G is also a function of temperature only. But when you derive this, delta G at equilibrium should be equal to 0. Using that definition, delta G of the product mixture or the, we will just say in general mixture, should be equal to 0. With that, I can also define Kp as partial pressure of CO divided by the atmospheric pressure. Please understand, it is the partial pressure of CO, not to the total pressure, partial pressure of CO to the atmospheric pressure raised to power the Stoichiometric coefficient of CO, which is 1, multiplied by partial pressure of oxygen divided by P naught raised to the stoichiometric value of O2. So, here 0.5. So, the numerator is the products of the partial pressure to the atmospheric pressure ratio to the power of the corresponding stoichiometric coefficients of the products, each product divided by the same for the reactants. In this, only one reactant is there. Reactant is for dissociation reaction, reactant is CO2. So, partial pressure of CO2 divided by atmospheric pressure P naught power 1.